Alright, here we are. This is the video for section 2.1. It follows pages 72 through 76 in our book. What we're going to be talking about today are relations and functions. Now, we're going to begin with relations. A relation is a mapping of input values with output values. More simply put, a relation changes one number into another number. Now, the number that you put into the relation, the input, all of the inputs make up the domain. We've heard that word before, domain. The output that you get out of the relation is the range. We've also heard that word. Now, you might know the word domain because we use it when we're talking about X. And you might know the word range because we use it when we're talking about Y. And it shows up that way in relations and in functions. Now, there are a lot of different ways that we can represent a relation. We could represent it as a set of ordered pairs, and if we do, an ordered pair would look like X, comma, Y in parentheses. Now, that means that all of these ordered pairs, these numbers, -2, -2, 0, and 3, are all the X values, which means they are all the domain. And if this is the entire relation, then this is the entire domain. Now, the 2, -2, 1, and 1 make up the Y values, so they are the range. And you can see these values are repeated here for the X values and here for the Y values. This is a chart. Now, a chart basically is exactly the same information as a set of ordered pairs, but we list it in this form. On your calculator, the graphing calculator, this is the form that you will see the points being listed in. The graphing calculator will usually not just give you the coordinate points. Although if we were to just put parentheses around this, these would all be exactly the same coordinate points. Another way you can represent a relation is with a graph. Now here we have a graph of the same set of ordered pairs. Now you can see our first ordered pair is -2, 2. And if we go to our graph, we see -2 on the x-axis and +2 on the y-axis is right here. -2, -2, again -2 on the x, this time -2 on the y. 0 and 1, since the x value is 0, it doesn't move, and the y value moves up to 1. And the last one, x is 3, so 1, 2, 3, and the y value is 1. So that's that point. This is a visual representation of the relationship. Now, the last way you might see it is as a mapping. A mapping is generally a couple of ovals or squares or circles with the numbers being listed inside. Now, as you can see, these numbers, -2, 0, and 3, are the same as my numbers here. The -2 is repeated in my ordered pairs and on my chart, so it's only listed once on the mapping diagram. 0 and 3 both show up. And the same thing over on the output, the Y values. The -2 here, the 2, and the 1. The 1 value is repeated on my ordered pairs and in my chart right here, but there's only one of them on the mapping diagram. And what the mapping diagram does for us is that it lets us visually see how the relationship works. We can visually see that the input -2 goes to both -2 and 2. We can visually see that both inputs 0 and 3, both of them go to the output of 1. Okay. Now, that's a relation. You can see a relation has some very general guidelines, right? A number becomes another number using a relation. Now, when we talk about functions, they're more specific. A function is a relation for which each input has exactly one output, and this exactly is important. Here we have two examples. Now we can see our input here, and we can see our output next to it. This is a mapping diagram. And what we can see is that -2 turns into -1, -1 turns into 0, 3 turns into 0, and 6 turns into 4. What we should notice here is that each one of my inputs, -2, -1, 3, and 6, all become one other number. -2 becomes -1, and so on and so forth. Now over in the other example, the output and the input are a little different. Here, -2 goes to -2, which is allowed. Even though it stayed the same, we would still call that a relation. 1 becomes 0. 2 becomes both 2 and 3. So here, one of my inputs, 2, becomes both 2 and 3. So it has two different outputs. That means that B is not a function. However, A is a function. And we can tell that A is a function because each one of my input values goes to only one number. Now, it doesn't matter that -1 and 3 both go to 0. That doesn't matter. We can repeat the output as often as we want. We just can't repeat the input at all. Okay. Now, graphically, if we were to plot the coordinate points on a graph, we can tell if a relation is a function if it passes the vertical line test. The vertical line test says that a relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. And we can illustrate that using this vertical line and these graphs. Let's start with A. Now, in order for this set of points to be a function, I need to be able to move this line across the graph and never touch more than one point at the same time. So, let's start it. Here we're touching one point, another, 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 and another. We get to the end of the graph, and yet at no point did this vertical line touch any of the any more than one point at any one time. If we look at example B, we can try the same test. The vertical line test says that if this is a function, my vertical line should only ever be touching one point at a time. So, we move it. Here it's touching one point. Here it's touching 2 points. At this spot, my vertical line is touching both this point here at 3, 1, 2, 3, 4, 5, 6, and 3, 6, and it's touching the point at 3, 2. Now we can see that the x values in both of these points are the same, which means that if we're given a set of x values, it should be no problem to look at that set of x values and determine if we have a relation or a function. If we have a relation, all that means is that each of the x values becomes a y value. It should be given. If it's a function, none of the x values are repeating themselves. All right. Many functions can be described as an equation in two variables, essentially what we've been saying. If we have an equation that has an x and a y, we have a function that is an equation in two variables, x and y. An example of that would be y equals 3x minus 5. Now, in this situation, y equals 3x minus 5, we have here the input, right? The x value is the input. And we have here the output. The y value is the output. Another term for input and output would be independent quantity and dependent quantity. The output depends on what we put in. So the output is dependent on the input. That means the output is the dependent quantity. The input does not depend on the output. So the input is the independent quantity. Now, an ordered pair, x and y, is a solution of a function if we can plug the x and the y in for the input and output and get a true statement, an equation that is correct. So, as an example, if I asked you, is the point 2, 1 a solution to this equation? And we can try that out. We can plug in 2 for x and 1 for y. If we plug in 2 for x and 1 for y, we have 3 times 2 is 6 minus 5. 6 minus 5 is 1. This is a solution. A function is considered a linear function if it can be written in this form, y equals mx plus b. Again, here we have input, we have output. M and b are just numbers. M and b can be any numbers, usually except 0. But usually there'll be some number. M will often be a fraction, and b will usually be a whole number of some kind. For instance, in this case, in the case of a, we can see we have f of x equals 6x plus 10. Well, we want to know, does this follow the form y equals mx plus b? F of x is function notation, and f of x quite literally means y. So f of x and y are the same thing. We have 6x. 6 could be considered m. So we do have mx plus 10. 10 could be considered b. So this is y equals mx plus b. That means that this function, f of x equals 6x plus 10, is linear. Now I have g of x. G of x is also function notation, and it still means y in this case. If we look at our equation, what we've got here is a number, another number, an x, and another number. What's different here, though, is that we have, and it should be fairly obvious, x squared. Well, our linear function template doesn't have x squared in it. It only has x. So, this is not linear. All right, one of the things that you're going to be required to do with linear functions, other than just telling whether or not they are linear, is substituting in values and finding the value of the function at a point. This is very similar to the evaluating that we did in section 1.2. So we're going to take the same two functions, f of x equals 6x plus 10, and g of x equals 2x squared plus 4x minus 1. Same two functions that we were just using. And we are going to evaluate them when x equals 2. Here's how we go about doing that. We want to know the value of this function when x equals negative 2. So we write it as f of negative 2. F of x becomes f of negative 2 because x equals negative 2. I have 6x plus 10, and just like we did in section 1.2, anywhere we see x, we're going to replace it with negative 2. So I have 6 times negative 2 plus 10. Now from here, I'm following the order of operations. The order of operations says that the first thing we would have to do in this case is multiply. 6 times negative 2. 6 times negative 2 is negative 12. We haven't done anything with the plus 10 yet. Negative 12 plus 10 is negative 2. So the value of f of x when x equals negative 2 is negative 2. And that is our answer. The function notation is useful in that now we can see the input here as f of negative 2, and we can see the output, what we got when we plugged in negative 2. So we see both the input and the output together. Now let's try it with g of x. We want to know what g of x is when x equals negative 2. So we start by plugging in negative 2 for x. And I have 2 times negative 2 squared. I'm going to put parentheses around it so that I know that I'm squaring negative 2 plus 4 times negative 2 minus 1. My next step would be to do the exponents. I have negative 2 squared. I have to get rid of the exponent. So negative 2 squared is positive 4. That means this is 2 times 4 plus 4 times negative 2 minus 1. Once I've done my exponents, I have to do my multiplication. I have 2 times 4, and I also have 4 times negative 2. So I'm going to do both of those multiplication steps at one time, going left to right. 2 times 4 is 8. 4 times negative 2 is negative 8. And minus 1 hasn't changed. Now I've got 8 and I've got negative 8. Well, as luck would have it, 8 and negative 8 are exactly the opposite. So when I add them together, they cancel out. And the only thing I'm left with is negative 1. That means that g of negative 2, replacing x with negative 2, is equal to negative 1.